not GK, 1.5 WK. So the stress distribution like this for wall 1, V1125 plus 400. 1125 is due to permanent loads, 400 due to self weight, divided by 0.25 kilonewtons per meter squared. $6,100 . Then we have to consider the wind load and wind moment. Wind moment is 3280 and the I is 2.6 multiplied by distance y, which is 5.0 divided by 2, MOI times y. That is 3280 divided by 2.6 multiplied by 2.5. 3153 kilonewtons per meter squared. So once you add them, multiply this by 1.0, multiply this by 1.5, and finally we'll end up with this type of stress distribution. Here the value will be 6,100. 6,100 plus 3153 into 1.5. So you get 10,829, and on this side we get 1,370. So from this we can say that no tension. The whole section is in compression. So wind load is not sufficient to cause tension, or we can say there's adequate self weight and the loads transferred onto the wall, so that no tension occurs. So that is one of the cases. Then out of all the other cases, I will consider this particular one, because we can see the wind, the stress due to wind is 3,153, and stress due to live load will not be that high because live load is only 300 kilonewtons per meter. So the most critical case for compression will be this one, not this one, because here the live dominates, here the wind dominates. So wind dominating case will be the most critical. So we'll look at that. So wall 1, we get 6,100 multiplied by 1.35, and due to dead and permanent. So variable, live, we get another axial stress, that is 300 divided by 0.25, get 1,200 multiplied by 1.05. How you get 1,200 is 300 kilonewtons per meter divided by the width of the wall. Then we also have this wind induced stress 3153 multiplied by 1.5 multiplied 1.5. So when you have consider all this, again you will get something similar to the earlier case, and you get 6100 multiplied by 1.35 plus 1200 multiplied by 1.05 plus 3153 multiplied by 1.5 with 14,224, and on this side you get minus 3153 multiplied by 1.5, 4765. Again, no tension, but you get a maximum compression of 14,224. And you can see all the other cases will be in between. So I will not consider those cases. And when you consider these two cases, when you compare these two, you can see this will be more critical than this one because we have an additional vertical load acting on this one. So this will be more critical than this one. Whereas because the wind load is dominating, this will be more critical than this one. So I have considered this for compression, I have considered this for tension, and I have not considered other ones. But there is a possibility that this may be governing, so we can check that. But because QK is not a dominating value, we can easily say this is also not governing, because when you compare this with this one, this will be more critical for compression than this one. So you can say that this one and this one will be governing, this one and this one will be governing. So we have the critical stresses with no coupling, right? Now what we are going to do is we'll have a look at the coupling case. We look at the problem again. Hence, determine the stress distribution that could occur under each wall. I have considered only wall number 1, and I have found the stress distribution. Then it asks what will be the moment resisted by each wall when the coupling action is effective. When the coupling action is effective, what is the moment resisted by each wall? Now we move on to next part of the problem. Here the coupling action is effective, and we are asked what is the stress distribution that you will get when the coupling action is effective. And for that, now we can see the next part of the problem. We have come up to 6. We have determined the stress distribution that could occur under each wall. I have considered only wall number 1. What will be the moment resisted by each wall when coupling action is effective? That is the next question. So we see the problem with coupling action being effective. When coupling action, the total moment M is 12,288. 12,288. And we want to find N. To find N, we need K alpha H that we found as 7.74. So now we have to find N, because we are now trying to see what's the coupling action. So we have to use this equation. N is equal to W h squared F1 over K squared L, and W is 6, H is 64, K is 1.08, and F1 is 7.74, somewhere here. So 7.74 somewhere here between 5 and 10, 7.74 somewhere here, let's say 0.38. So this F1 factor is 0.38. So N is equal to W 6, H 64, F1 0.38, K squared 1.08 squared, multiply L 8.5. So that gives an N value of 6 into 64 multiplied by 0.38 divided by 1.08 squared divided by 8.5. So you get again 64 squared multiplied by 64, 941 kilonewtons. So M1 plus M2 is equal to M minus NL, and that gives 12,288 minus 9.941 into 8.5. So that gives 12,288 minus 941 multiplied by 8.5. That gives 4,289. And that also gives M1 as 2.6 divided by 9.74 multiplied by 4289, and that is M is equal to I1 over I1 plus I2 times M1 plus M2. So this gives so you can see the values. N is equal to 941, and M1 plus M2 is M minus NL. That is 12,288 minus 941 into 8.5. That is 4,289. And M1 is equal to 2.6 divided by 9.74. That is I1 divided by I1 plus I2 multiplied by 4289. And 2.6 divided by 9.74. So you get 1,145. Now you can see the effect. The coupling action, before the coupling action, the moment was 9,280. Now the moment has reduced to 1,145. 1,145. So you can see the effect of coupling action. Is that clear?
Yes, sir.
Right. Now we can move to the next step. And we are asked to find the stress distribution with the coupling action. So with the coupling action, we have to be a little careful. And there's a reason for that. Now again, we are going to find the stress distribution. We'll consider similar to the earlier case. 1.0 GK plus 1.5 WK. Case, that is ball number 1. Ball number 1, similar to the earlier case that we considered, and 1.0 GK does not change for ball 1, and it remains as 6,100 kilonewtons per meter squared. And then, so this is compression. Then we get a tension which is equal to we just calculated the load due to coupling action, which is 941 kilonewtons. Just calculated this value due to the coupling action. We just calculated this value 941. So here you get 941 divided by 5 divided by 0.25, giving divided by 5 divided by 0.25, giving 752 kilonewtons per meter squared. And this is in tension. The reason is on this side N is this way, this side N is this way. So this tension plus we get the bending moment effect, and that is again from the earlier case. Here you get 3153 multiplied by 1.5. So what can you say about this tension? Do you have to multiply it by a factor or not? Do you have to multiply it by a factor or not? Yes, we have to multiply it by a factor because it's in tension. And this side also we get tension, because we are considering it as 1.5 times the wind load. And wind load is the one that is causing this particular tension. So we have to multiply it by 1.5. So here also you get 1.5. So that will finally give us stress distribution of 6,100 minus 752 multiplied by 1.5. Oh, sorry, this is not 3153. I made a mistake because this moment is 1145 now. So the 1145 divided by 2.6 multiplied by 2.5. So this is 1100. 1100. So we get 6,100 plus 752 into 1.5 plus 1,100 multiplied by 1.5. So we'll end up with 6,100 plus 752 into 1.5 plus 1100 into 1.5. So you get 8878. And on this side you get 6,100 minus 752 into 1.5 minus 1100 into 1.5. 332. And if you compare that with the earlier stresses, earlier we got 1370. Earlier we got 1370. Now we are getting 3322, which means the effect of tension is reduced. And if you look at the compression, that also has reduced. That also has reduced. Compression has reduced, tension has reduced. So, which means the coupling action has a definite advantage. Coupling action has a definite advantage. Then we can also consider the other critical case, and that is dead permanent, or the permanent 6100 multiplied by 1.35, and then we get tension again, live load 1200 multiplied by 1.05, and then we get tension happening like this compression, this tension 752 multiplied by 1.5, and also we get wind, that is 1100 multiplied by 1.5. So finally we'll end up with a stress diagram like that, which gives 6100 into 1.35 plus 1200 into 1.05 plus 752 into 1.5 plus 1100 into 1.5. So you get 12,273, and earlier we got 14,224. Here now we are getting 12,273. Earlier we got 14,224. Now we are getting 12,273. Whereas on the tension side, earlier we got 4,765. Now we get 6,100 into 1.5 plus 1,200 into 1.05 minus 752 into 1.5 minus 1100 into 1.5. So we end up with 7632. So you can see it's better with tension as well. Earlier you get a lower compression, which means there's a chance for going into tension if the wind load is high, whereas here we get a higher value. Now you can clearly see the effect of coupling action when you compare these two, and you can clearly see the effect of coupling action. Coupling action will actually reduce. You can clearly see the effect of coupling action, and coupling action is actually reducing the effect of tension, and also it's reducing the maximum stress. When you keep it side by side, you can clearly see the situation. Because I have considered the most critical two load cases only, I have omitted the ones that may not be governing. So you can clearly see what's going on here, and so with that you can see the effect of coupling action. So this is the example, and then we will go back to the note and see what are the other things we have been asked to do. Right, you can see the note now. So let's see. So we have found the moment resisted by each wall when the coupling action is effective. Then we have been asked to determine the stress distribution that can occur in each wall when the coupling action is effective. We have found it only for wall 1. Determine the maximum forces that could act on the coupling beam and comment on the reduction. Determine the maximum forces that could act on the coupling beam, and then comment on the reduction in deflection that would be possible with coupling the shear wall. So we'll see the last two parts. And we have been asked to find the force on the coupling beam. And for that, we have to actually get back to the knot. So now we have to go for this one, the force on the coupling beam, Q. So we want to find the value of Q, and Q is given by WH K squared L and F2, and for K alpha H of 7.7, somewhere here, we have to go on a curve parallel to this 8 curve, goes like this, and here you can see F2 max occurs here at this particular point, where this curve, which is 7.72 curve, goes like this. This is 5, this is 8, 7.72 goes like this. So here you can see the maximum value of F2 is about 0.58, and the height at which this occurs is 0.27 times h. 0.27 times h, and that is the beam where this occurs. H is 64, 0.27 times 64. So this occurs somewhere around 17.28 meter height, maximum value of Q, and F2 is 0.58. F2 is 0.58, somewhere. It's about 0.58. So Q is equal to W6 into 64 into F2, 0.58. K squared is 1.18 multiplied by 8.85. 8.5, not 8.85, 8.5 is there. So you get a Q value of 6 into 64 to 0.58 divided by 1.18 divided by 8.5. The maximum value of Q is 22.2 kilonewtons per meter. So I'll stop share and show the screen to you. Right, so this is what you get. Q is equal to WH K squared over L F2. F2 is 0.58. So once you substitute, you get Q as 22.2. But the important thing you have to remember is Q is given as 22.2 kilonewtons per meter. So if you want to find capital Q, that is the max actual shear, you have to multiply it by 3.2, which is the flow to flow height. 3.2 is the flow to flow height. So 22.2 multiplied by 3.2 will give you 71 kilonewtons shear force. So we have a coupling beam, and it is subjected to a shear force of 71. And we can find the corresponding bending moment is 71 multiplied by 2.5 divided by 2, because there's a point of contraflexion or zero moment at the middle. So the bending moment is equal to shear force multiplied by the lever arm, and that gives you a value of 71 into 1.25. So that gives you a bending moment of 88.75, which is not a big moment for a coupling beam of size 700 millimeter depth and 250 millimeter width. Then you will ask, how do you provide the reinforcement in coupling beams? Generally in coupling beams, what happens is, in case of earthquakes, sometimes these coupling beams can fail here due to the formation of plastic hinges. So this is the wall, this is the wall. Wall is very rigid, beam is not that rigid. So plastic hinges can occur here. So when this happens, we run into a major problem, because now you know with the coupling action we have designed this wall to resist the bending moment of only 1145. When there is no coupling action, the moment is 32. Moment is 280. So what will happen to this coupled shear wall in an earthquake if the coupling beam fails? If the coupling beam fails, it will move from this to this. So the wall is designed to carry only 1145 kilonewton meters, but when the coupling beam fails, the moment becomes 3280. The moment becomes 3280. So what could happen to the coupled shear wall? The coupled shear wall might fail. We cannot always say it will fail. It might fail because shear walls have very high in-plane moment capacity. So there's a chance still the wall might survive, but it's not a good situation. So the solution is this. So what we do is, in addition to providing the normal reinforcement, we provide some additional diagonal reinforcement as well. So we provide some diagonal reinforcement as well, like that. And then you have to find the amount of diagonal reinforcement. For that, we go for a force triangle. So this is the shear force Q, and this is resisted by a tension and compression in these diagonal struts, which is actually reinforcement. So C and T, and we have to find alpha, and in this case tan alpha is equal to these 700, and the span is 2.5 meters. So we get tan alpha is 700 divided by 2500, and alpha is equal to 700 divided by 2500. 15.6 degrees, and so this is alpha. This alpha Q is equal to 2t sine alpha, and from this we can find t is equal to Q, and in this case Q is 88.75 divided by 2 sine 15.6, and from that we can say T is equal to 88.75 divided by 2 divided by sine 15.6, we get 165 kilonewtons. And if you consider 32 diameter bar, the area of a 32 diameter bar is 804 square millimeters. So, and 0.87 times 804 multiplied by 500 will give us the load that this bar can carry, 0.87 into 804 into 500. So it can carry a load of 349 kilonewtons. So we can actually provide a 32 diameter bar diagonally, so that this bar will be able to resist the shear that is transferred from the wall to the coupling beam. So in case of an earthquake, we can make sure, because we have the normal reinforcement and the additional diagonal bars, this coupling beam will not fail easily. So we generally provide these diagonal reinforcement in coupling beams to prevent the shear failure that can lead to the formation of plastic hinges at the beam wall junction. Beam wall junction is, this is the wall, and here this junction you can get these additional plastic hinges forming in case of ultimate situations. And to prevent that happening, we generally provide this diagonal reinforcement as well. So that is some additional information for you. And can you understand this particular additional part? Or any questions that you want to ask?
Sir, the
Yes.
excuse me, sir. Can you hear me?
Yes.
The Q is 71. No?
Sorry?
Q is 71 kilonewton, no, sir.
Two.
Not 88.75. Q is equal to 2t sin alpha. You have Q as 88.75. But
Q is the shear force, is it?
71 kilonewton.
Oh yes. Oh sorry, not bending moment. Sorry, I have something to bending. This 71, isn't
Bending
it?
moment is the 88.
Yeah, 71. This 71 divided by 2 divided by sine 15.6. So it is 132 kilonewtons. Is that right? So I could have actually provided even a 25 millimeter bar, right? That is your question, is it? Have I answered the question?
Yes, sir. Yes, sir.
Sorry about that mistake.
Yes,
I have
sir.
substituted the value of bending moment instead of shear force. So any other question you want to ask? And then we can also look at the last part. And then comment on the reduction in deflection. So comment on the reduction in deflection. So K is 1.08. K alpha is 7.7. Somewhere here. So what is the deflection that you can expect? Only 20% of the deflection that occur in the wall without coupling action. The deflection that you get is only 20% of the deflection that you get without coupling action. So the K value is 1.08 somewhere here, and this is 7.7. Then when you come this way, you get 0.2. So the deflection is only about 20% of the deflection that you get in the actual case without coupling action. And if you want to find the deflection without coupling action, that is given by W h to the power 4 divided by 8 EI. And what is the elastic modulus of concrete? Which is about 25,000 megapascal or kilonewtons per meter squared, or 25 kilonewtons per millimeter squared. So you get W as 6 and height is 64 to the power 4. 8 E value should be in kilonewtons per meter squared. So that is 25,000 multiplied by 25 multiplied by 10 to the power 6, and I value is addition of I values is 9.74. So the deflection in millimeters is 6 into 64 to the power 4 divided by 8 divided by 25 to the power 6 divided by 9.74. So you get a deflection of 0.051 or 51 millimeters without coupling action. And then when you have the coupling action, the deflection will be 20% of that, which will come to only about 10 millimeters. So this is the deflection. Deflection is given by WH to the power 4 divided by TI and is 25,000 megapascal or 25 kilonewtons per millimeter squared or 25 into 10 to the power 6 kilonewtons per meter squared. So you have to substitute in kilonewtons per meter squared. So that's why I chop this off. And I value is 9.74. So you get 51 millimeter deflection without coupling action. But with the coupling action, it reduces to only about 20% of that. Is that clear? The effect of coupling action. So I have shown few important things. One is what happens without coupling action and the possibility for tension to occur if the wind loads are high enough or the axial loads are low enough. Then we looked at the coupling action and we found that additional tension occurs due to the coupling action, but that effect is not very serious because the additional axial force that is transferred is not very high, but the reduction in moment is very high. So we get although we get additional tension, still the resultant tensile stresses or the minimum compressive stresses are better than the earlier case. And when it comes to the maximum compression, there's a reduction in the maximum compression as well. So those are our observations, which shows us coupling action is very effective, and whenever possible, we should consider harnessing it by having connecting beams. So any questions on this? So I'll upload the note as well. So any questions on this?
Excuse me, sir.
Yeah.
So that additional tension occurred due to the coupling action. Why did we add that to the compression? Do we have to?
No, I didn't add it. I actually deducted it. Yeah, you can see I actually considered as here you can see I consider it as tension.
Yes, sir.
So I added this, deducted this for this side. For this side, I have to deduct it and add it. So what is the answer? Have I made a mistake? 6,100 into 1.35 plus 1,200 into 1.05 minus 752 into 1.5 plus 1,100 into 1.5. I think I have made a mistake. Yeah, 10,000. This is actually not 12,000. This is 10,017. So
In the above one also, sir.
clearly indicate which is tension, which is compression. Otherwise, you can make a mistake. Okay.
In the above one also we did that, sir.
I did that.
Yeah. Yes, sir. 8,878. Just above line. 8,800.
Yeah. That side also. So that is this is minus, this plus. Okay. So always mark tension and compression, then you will not make a mistake. 6,900 minus 752 into 1.5 plus 1100 into 1.5. Then you get 6622. Okay, thank you for highlighting that. Huh? Okay. So the important thing is, mark compression tension, then you will not make a mistake. So I did not mark it, so I made a mistake. Okay. Is that clear? Always mark tension, compression, because we are getting tension and compression both. Is it okay?
Yes, sir.
Yeah. Any other question like that? Thank you for highlighting that. So when you keep this side by side, now it's clear. Okay, so you can see a drastic reduction in the compression because of this tension action. But on the other side, 7 meter long ball, you will get compression. So although here it's reduces, that side there will be a slight increase. Is that clear? On the other side, this is not tension, the axial force is compression. So shall we do a calculation on this as a quiz, where you will do the calculation for both the ball 1 and ball 2? Are you convinced this coupling action is working? It has advantages. Okay, with that, shall we conclude the lecture?